All right, folks, today you are going to get a crash course in the periodic table. Let's go. First, I want to talk about two materials that you may know of that are pretty important: diamond and graphite. Graphite is the material that you find in pencil lead. Diamonds, you know them as that object that you have to buy somebody, where the amount that you love somebody is determined by how expensive and how big that object is. And they are both made of carbon, pure carbon. That's C on the periodic table. It's the same element. How can something so expensive and so valuable be made of the exact same material as something like graphite? Well, it has to do with their structure. The way the atoms are arranged are different in diamond versus graphite. Both of them are made deep in the earth. When carbon, which comes from plant and animal matter that died long time ago, it gets buried and then put under high pressure and temperature, and inside the earth it gets formed into either graphite or diamond based on that temperature and pressure. Now you can actually do this synthetically and make your own diamonds. I was just reading about this. It's actually a thing these days. I don't think it was really possible before, but now they have the technology to do it. And synthetic diamonds are just like natural diamonds, except they're not made naturally. And, for that reason, they're probably, people don't want them as much, but they're the exact same as natural diamond and just as beautiful, I think. So, anyways, they're both made of carbon. Now, today we're going to learn about what we mean by when we say a carbon atom and what's inside an atom. But in order to do that, we need to use a model of the atom, which brings us to the question, what is a model? We're going to discuss this and answer this in class. And for now, I want you to think of your answer that you'll provide when I ask you, what is a model? Well, one model of the atom was developed by Niels Bohr, and it's called the Bohr model. Now, Niels Bohr, he lived from 1885. That's, I think, very close to the middle or the end of the American Civil War. Died in 1962 after the drop of the atomic bomb and well after the conclusion of World War II. And he developed the planetary model. He was the first to propose this in 1913. And in that model, it proposed that atoms have a nucleus and that they're orbited by electrons, that they go around and around. Now, you just have to know that at this time, this was actually kind of a revolutionary proposal. Many people didn't, before that, atoms were kind of thought of just hard spheres. And then we started to discover that there's actually a lot of empty space inside atoms, and they're not just hard spheres. Well, that planetary model really took off. Now, this isn't how atoms actually behave. Electrons don't actually circle the nucleus like a planet orbiting the sun, but we still use this model because it helps us to learn about important features about the atom. Let's dive into this model in detail. In your notes, I want you to draw this with me. First, I want you to draw some protons. And then I'm going to draw some neutrons. So the plus signs, these are protons. And I'm going to label them as protons. I'm also going to draw some neutrons, which I'm not going to put anything in the center. They have no charge. They're neutral. These are neutrons. And they are all in the nucleus. Now, surrounding the, and you know what? Really, what I want to do is just point out that the nucleus is this whole thing. And I think actually the best way is just to leave it like that. So we have these is the protons, these is the neutrons, and this whole thing is the nucleus. Now, surrounding the nucleus are going to be electron shells. So I'm going to draw a circle. This is an electron shell. It's also known as an orbital, kind of like orbit. That's where it got its name. It's an orbital. And that's where electrons hang out. And I'm going to denote an electron by drawing a circle, doing a minus sign. And then these guys are electrons. And electrons are on the outside. Now, there's a couple things that I want you to know about protons and electrons. So first of all, protons have a positive charge. That's from the plus sign. Electrons have a negative charge. What do I mean by positive and negative charge? Well, if I took a proton and I took an electron, they would actually attract each other. Positive attracts negative. This is kind of like magnets, and it's kind of like opposites attract. This is always the point where I like to describe Mrs. Wu as somebody who is completely opposite of Mr. Wu. I mean, she's so different. She's sarcastic. I'm not sarcastic at all. She's brilliant. I'm not that brilliant. We're complete opposites. She is my better half, I will say. Opposites do attract. And I will say that that's what you need to know is that opposites, plus and negative, they attract each other when it comes to atoms. Neutrons are neutral in charge. That means they have no charge. Now, when it comes to the number of protons, so this is the number of protons, the number of protons is going to be equal to the number of electrons in a neutral state. So if I have 3 protons, I'm going to have 3 electrons. And actually, I'm going to draw on another ring because you'll learn later that I can't have 3 electrons on the first ring. So I have 3 protons. If I have 3 protons, I have 3 electrons if my atom is in a neutral state, meaning the atom itself doesn't have a charge. Neutrons are the glue. They hold the nucleus together. And the more neutrons that I have, usually they act as stronger glue, although sometimes, as you're going to see, there is a limit to the amount of neutrons that we can have. They act as the glue. They add bulk to the nucleus, and they help stabilize it. Now, when we look at the periodic table, the number of protons determines the element. Meaning, if I have 1 proton, that's hydrogen. If I have 2 protons, that's helium. The number of protons is the only thing that tells me whether or not I have hydrogen, helium, or any other element. It's all determined by the number of protons. And those increase by 1 from left to right on the periodic table. So every single element, as I move up the periodic table, and that's from left to right, I'm increasing by 1 proton. And that's the only thing that determines what the element is. Now, if I look closer to a box on the periodic table, I'm going to notice a couple of things for each element. first, you're going to have the official element name. Oftentimes, these are named by the scientists who discover them. So imagine an element name. If I discovered an element, it would be called something like, I don't know, Dr. Wuium or Wuium. Does that sound like a good name for an element? You will also see this number, and it's the lower number versus the other. There's two numbers, and one's going to be smaller, and one's going to be a whole number. That whole number is the atomic number. You're also going to see one or two letters, which is going to be its atomic symbol. You're also going to see a number with a decimal, which is the atomic mass. Now, let me give you some details here. The atomic number is the number of protons. It tells me how many protons an element has. The atomic number is also the number of electrons in a neutral state, because the number of protons and the number of electrons will be the same. The atomic mass, which is the number with the decimal, is the number of protons plus neutrons. However, it is an average value. Protons and neutrons are always whole numbers. So if I have a mass of an atomic mass of 95.94, I'm going to round that to 96. And this means I'm going to have 42 protons and 54 neutrons. We're going to practice this more, so don't worry about it too much right now. But I just want to explain that the reason why this is a decimal instead of just a whole number, 96, and we have to round it, is because it's an average value of different elements with different masses called isotopes. And that's because in different isotopes, the number of neutrons can vary. We could have molybdenum with 54 neutrons. We could also have molybdenum with 42 protons, which makes it molybdenum. So it has to have 42 protons. But instead of 54 neutrons, we could have 53 neutrons. And you will find this in nature. And its mass would no longer be 96, it would be 95. And because we can find them in nature and they're naturally occurring, they take an average between these two numbers based on how much of that particular isotope you will find to come up with this decimal. And this decimal tells me that most of it is molybdenum 96. And very little of it is molybdenum 95, although there are some of that in nature, and those are called different isotopes of molybdenum. You'll learn more about that in chemistry. All you need to know for now is that for now, we just round the atomic mass straight up to 96, because we use this number right here to round it to the nearest whole number. So I look at this number. And so atomic mass is the number of protons plus neutrons. And that's measured in AMU, which is called atomic mass unit. Let me just say one quick thing about atomic mass units. A proton, one proton, has a mass of 1 AMU, or 1 atomic mass unit. 1 neutron weighs about 1 AMU, atomic mass unit. 1 electron, its mass is very close to 0 AMUs. It's very, very light. It has almost no mass. This is how we measure mass, and neutrons and protons, which are in the nucleus, have the bulk of the mass that you'll see, and electrons don't have much mass. That's why they can zip around so quickly. What is AMU? Well, 1 AMU is defined as 1/12 of the mass of a carbon atom. And a carbon atom is made up of 6 protons and 6 neutrons. So 1 AMU is basically the mass of either a proton or neutron, although it's not exactly that. You don't really need to know the details on that, and you will probably learn more about that in chemistry. But for now, all I want to say is that you do need to know that protons and neutrons are the only components that have mass. Their mass is about 1 AMU, and electrons in comparison have almost no mass. We're going to say it's 0 AMU. Finally, I want to give you a little mnemonic device that's going to help you remember how we come up with number of protons and neutrons and electrons. And it's called Ape Man. And no, I'm not making reference to a 1980s, 1990s movie where somebody wakes up on a planet full of apes, but then discovers something startling about the planet he ends up on. Watch it. It's called Planet of the Apes. It's a classic. Although honestly, I haven't seen it, so I don't know why I'm telling you to watch it. Anyways, Ape Man, this is what it's going to look like. The number of the atomic number, this is my A, is equal to the number of protons and the number of electrons. They're the same number. It's the number of protons and the number of electrons. They're the same number. For man, that's talking about atomic mass. So atomic mass, for example, when we had molybdenum, which was 95.94, and I round that to 96, that's going to be equal to the atomic number minus the number of neutrons. And basically, we use this to figure out the number of neutrons. So, for example, actually, no, this is the atomic number plus the number of neutrons. I'm sorry. The atomic mass is the atomic number plus the number of neutrons. And for example, for molybdenum, it was 96 was the atomic mass after we rounded it. The atomic number was 42 plus the number of neutrons. So if I subtract 96 minus 42, my number of neutrons is 54. That's Ape Man. I take the atomic mass minus the number of protons, the atomic number, and it gives me the number of neutrons. And that makes sense because the mass is the number of protons plus neutrons. That's basically it for today. The next thing we're going to do is an activity in class where we go to tinyurl.com/CT-BORATOM, and you should follow the instructions on your handout to learn more and explore about the atom.